Today, we are diving into a huge crisis happening right now at the very heart of physics. It's a mystery so profound that it's forcing scientists to literally tear up their most trusted maps of reality and ask a terrifying question. What if we've been looking at the universe all wrong?
Think about it. For centuries, we've been following this one single map, and it's been spectacularly successful. But now, that same map has led us to a place that, according to the map's own rules, shouldn't even exist. So what do you do? What happens when your trusted guide is telling you something that seems fundamentally impossible? All right, so our story begins with the absolute triumph of a really powerful idea, and the one tiny, impossibly perfect discovery that, well, brought the whole thing crashing down. For generations, physics has been guided by this one simple, really intuitive principle: reductionism. The idea is, pretty straightforward. If you want to understand a galaxy, you study the stars. To understand a star, you study atoms. To understand an atom, you study its subatomic parts. It's kind of like a perfect set of Russian nesting dolls, with the ultimate truth of everything hidden inside the very smallest one. And you know what? This approach worked brilliantly. It allowed us to peel back the layers of reality and build what we now call the standard model of particle physics. And you could argue it's the most successful scientific theory in all of human history. It describes the 17 known elementary particles and how they all interact with just stunning precision. So in 2012, when scientists discovered the Higgs boson, that was it. That was the final crowning achievement. It was like the keystone that locked the entire structure of the standard model into place. It was a moment of absolute triumph. But it also revealed this deep and really troubling crack in the foundation. And here's the problem. The Higgs boson's mass, it just makes no sense. According to all our theories, it should be trillions of times heavier than it actually is. It's so unexpectedly light that physicists literally have a special word for it. They call it unnatural. This whole puzzle is known as the hierarchy problem. To really appreciate just how big this problem is, think about this. The Higgs interacts with everything, including all the crazy quantum stuff happening at the highest possible energy level. That's called the Planck scale. And all those interactions should be feeding it just enormous amounts of energy, pushing its mass up to this colossal number, 100 million billion times larger than what we actually see. So for the Higgs to be as light as it is, all of those gigantic positive forces pushing on its mass and all of the gigantic negative forces pulling on it have to cancel each other out with near-perfect precision. It's like balancing a pencil on its sharpest point, and it just stays there. Forever. It's possible, I guess, but it's so wildly improbable that it feels like some kind of cosmic conspiracy. Physicists call this fine-tuning.
And this just brings the whole problem into super sharp focus. The expected mass is astronomical, but the measured mass is this tiny, delicate 125 giga-electron volts. To put that into perspective, it's like expecting a bowling ball and getting a feather instead. The universe appears to be fine-tuned to an absolutely absurd degree, and for a physicist, that is a giant, flashing red flag that we are missing something really big.
So the hunt was on. Physicists were pretty confident they knew what that something big was, and they went and built the most powerful machine in human history to go find it. The leading idea was this beautiful theory called supersymmetry, or SUSY for short. It proposed that every single particle we know about has a heavier super partner out there. And crucially, these partners would contribute to the Higgs mass in the exact opposite way, naturally and automatically canceling out all those huge corrections. No fine-tuning needed. It was elegant, it was powerful, and pretty much everyone was convinced it just had to be true. For 3 decades, this became the central quest of particle physics. An entire generation of scientists dedicated their whole careers to finding these superparticles, and it all culminated in the construction of the $10 billion Large Hadron Collider in Geneva, a machine built for this exact purpose. And after years and years of smashing protons together at unimaginable energies, what did they find? Nothing. Absolutely nothing. No superpartners. Not a single one. Supersymmetry, the beautiful idea that was supposed to save everything, it just wasn't there. The crisis was no longer some quiet concern in the background. It was a blaring alarm going off for the whole world to hear. This failure, this nothing, forced physicists to do something really radical. They had to start questioning their most basic assumptions about how the entire universe is put together. Maybe that nesting doll model was just broken. And you can really feel the gravity of the situation in this quote from Gidan Giudici, who's the head of theory at CERN, the home of the LHC. He basically said that the failure to find new particles meant it was time to reconsider the core principles that had guided physics for half a century. So this has led physicists to explore some pretty wild new ideas that completely break that reductionist model. One of the biggest ones is called UV-IR mixing. So the old nesting doll idea assumed that the physics of the very small, high-energy stuff, the UV, determines what happens at the large, low-energy scales, the IR. But what if the influence flows both ways? What if the universe as a whole, its largest structures, could somehow reach all the way down and constrain what's even possible at the very smallest level? Now, this isn't just wishful thinking. We already know of one force that behaves exactly this way: gravity. See, if you smash particles together with enough energy, you don't just keep finding smaller and smaller pieces. Eventually, you create a black hole. High energy leads to a large object. Gravity is fundamentally anti-reductionist. And from this new perspective, maybe the unnaturally small Higgs mass isn't a fine-tuning problem at all, but a sign that some large-scale cosmic rules are at play that we never even considered. But exploring new physical principles is just one path forward. There's another, even more revolutionary idea that's taking hold. One that suggests the problem might not be with our theories at all, but with the very limits of what can be known. This path leads us away from particle colliders and straight into the foundations of logic and computation. Some physicists are now starting to believe that we might be running into fundamental limits not of our technology, but of what is even knowable in the first place. The core concept here is something called undecidability, and it was first formalized by the great Alan Turing. An undecidable problem is one where no algorithm, no computer program can ever be written that is guaranteed to give you a correct yes or no answer for every possibility. The classic example is the halting problem. There is no general program that can look at any other program and tell you for sure if it will eventually stop or just run forever. And here is the absolutely wild part. These aren't just abstract thought experiments anymore. Undecidability is now showing up in real, concrete physics problems. For example, it's been proven that for some quantum materials, the question of whether they have a spectral gap, a really fundamental property, is undecidable. There's no universal algorithm that can answer it. It's even been shown that for some theories, the question of whether supersymmetry is broken is itself undecidable. We may have been searching for answers to questions that are, by their very nature, completely unanswerable. So this isn't an ending. It's not the death of physics. Far, far from it. This crisis is actually the painful but exhilarating birth of a whole new scientific frontier. Instead of despair, many people in the field feel this incredible sense of excitement. As the theorist Isabel Garcia Garcia puts it, the failure of the old way of thinking means that we are on the verge of discovering something truly new and profound about the nature of our universe. And this leaves us with a final, just fascinating thought. For over a century, physics has operated on this belief that with a big enough machine and a smart enough theory, all of nature's secrets could eventually be revealed. But maybe the greatest discovery of this century won't be a new particle at all, but a new appreciation for the limits of knowledge itself. An understanding that some truths might not be hidden answers waiting to be found, but fundamentally unanswerable questions.